We can start now.
Okay, thank you. Let's start. So the local structure theorem, which I recall here for your convenience, tells us roughly that locally a spherical variety is isomorphic to a product of an affine space and an affine spherical variety for a smaller group. This is because of this direct product decomposition for the open B chart, because this first factor is the unipotent group, and the unipotent group is isomorphic via the exponential map to its Lie algebra, which is just an affine space or a vector space, if you like. This is this first factor. And the second factor is, as we proved in the local structure theorem, is an affine spherical variety with respect to the action of the Levy subgroup of this parabolic P. So this second factor is L in this decomposition. And since the G translates of B charts, open B charts cover the whole spherical variety X, we have locally this kind of decomposition. So many issues about spherical varieties are reduced to the affine case.
Professor, sorry.
Yes.
So how do we prove this is normal last class?
I think that this question was already asked at the previous lecture. So the normality is explained very easy because X is normal by definition. It is a spherical variety. And this open subset is also normal because it is an open subset in X. It is also normal. And since we have this kind of product decomposition, the first factor being just an affine space, since this guy is normal, this is also normal. Okay? So normality is not a problem here. Now, let me tell you that there is a subclass of spherical varieties for which the local structure is even nicer. Let me give you a precise definition for this subclass. So definition. A spherical variety X is said to be toroidal another name for it is colorless. Toroidal or colorless. If no color in X contains a G orbit, so any color B does not contain any G orbit. In other words, you may reformulate it differently. In other words, for any G orbit Y, the set of colors containing Y, which we denoted like this, D over Y, is empty. For any G orbit Y in X. So these are toroidal varieties. And in the notation of the local structure theorem, we have the following. The variety X is toroidal if and only if the slice Z in the local structure theorem is toroidal. Well, for any G orbit, of course, for any G orbit Y, the slide Z is toroidal. Because the colors in Z are identified with a certain subset of colors in X. The subset of colors containing Y and not preserved by the action of P. Since this, if this set is empty for all Y, this set is also empty. So Z is also toroidal. And also Z is affine. And this implies that actually every regular function. Yes. Yes.
Isn't they always affine?
Z is always affine in the local structure theorem. Just well, because it is a closed subset in an affine open subvariety.
Wait, yes, I know. Since G is affine, why do we write again that?
Well, just to emphasize, I mean, just to emphasize that this condition is important for the sequel, for what I'm going to tell you now. So this is just an addition. This is not because of X is toroidal. Yeah. So X is toroidal if and only if Z is toroidal. And this implies, since Z is also affine, that every regular function on Z, which is semi-invariant with respect to the Borel subgroup of L, is actually semi-invariant with respect to L itself. The set of B intersect with L semi-invariant functions, regular functions on Z, coincides with the set of L semi-invariant functions. Indeed, given such a function f, we have that the divisor of f in L is stable under B intersect with L. But there are no colors, so every divisor which is stable under the Borel subgroup, not that there are no colors, there are no colors containing the closed orbit in Z. But as we discussed here, all B-stable divisors in Z contain the closed orbit. We have proved this in the course of proving the local structure theorem. So there are actually no colors in Z, and therefore this B intersect with L stable divisor has to be L stable. And since the divisor is L stable, the equation defining this divisor, this function f, has to be L semi-invariant. So every semi-invariant regular function for the Borel subgroup of L is also semi-invariant for L itself. And this implies immediately that the derived subgroup of L acts trivially on the algebra of regular functions. Because what are semi-invariant regular functions with respect to the Borel subgroup? They are exactly the highest weight vectors for irreducible representations of L in the coordinate algebra of Z. And since all these highest weight vectors are L semi-invariant, the respective irreducible representations are just one-dimensional. So the coordinate algebra of L decomposes in a direct sum of one-dimensional irreducible representations. This means that the derived subgroup acts trivially because this subgroup has to act on each one-dimensional summand by a character. But there are no characters, there are no non-vanishing characters on this derived subgroup. Every character takes identically the value 1 on the derived subgroup. So the derived subgroup acts trivially on the coordinate algebra of Z. And this in turn implies that it acts trivially on Z itself, because Z is an affine variety. And an affine variety is completely determined by its coordinate algebra. So this implies that the action of L on Z goes through the action of the quotient subgroup, L over the derived subgroup of L. So actually L acts on Z via this quotient subgroup. And this quotient subgroup is a torus. So this means that Z is a toric variety. We conclude that locally a toroidal variety is isomorphic to the product of an affine space and a toric variety. Well, affine toric variety.
Isomorphic or bidirectionally equivalent?
No, just isomorphic. Isomorphic. Locally isomorphic. Locally. Yeah.
Professor, I want to ask a question. So we do have that X toroidal, that then we have G toroidal, but why the inverse is always also true?
Inverse is not always true. I mean, I didn't say that. I didn't say
so what
that.
The first line of in LST mean? Well, this is a double.
You mean yeah. I mean this equivalence. Yeah. So let me think a little bit. So if Z is toroidal, then this means that let me turn back to the previous page. If Z is toroidal, this means that this set is empty. This means that every divisor, every color containing Y is p-stable. Well, this may happen. I mean, there is no reason for that not to happen. It may happen.
So there may.
So this means that actually there is no equivalence here. Yeah, just an implication. So thank you for this comment. Indeed, it is safe to state here that there is just an implication from the left to the right. Okay. So we cannot guarantee that X is toroidal if Z is toroidal for every Y. What we can guarantee is only that this set is always empty, which means that every divisor, every color containing the orbit Y is p-stable. And this, well, this may happen. Okay?
Okay.
Okay.
And there may be some other questions. Well, I will want to see the next page.
Yeah.
So the second implication is
the second implication is explained here. So if you have any function, regular function, which is B intersect with L semi-invariant, then its divisor is B intersect with L stable. And since there are no colors on Z,
so
this divisor
in the.
Excuse me?
Well, the comma between toroidal and affine is just like a prime for L.
You mean this comma? No, this is a comma. This is a comma. This is not a prime. This is not a prime. This is a comma for the previous line. I mean, I don't know how to put it like here. Okay. This comma is related to this line, not to this one. Any more questions?
So this means that well, I want to think about the third implication.
Okay. Just think about it, and later you can address your question. So let me emphasize that the local structure theorem, so the previous remark, this remark in the toroidal case implies that we have the following local decomposition, local isomorphism. So each toroidal variety is locally isomorphic to a product of an affine space and an affine toric variety, so the Z. And this affine space is Pu on the previous slide. But also let me observe that each affine space is also a toric variety, just for the action of torus by dilations, by independent dilations on each coordinate. And the product of two toric varieties is still a toric variety. So you may also say that toroidal varieties are locally toric. This explains this name toroidal for them. And the name colorless is also clear because you know that a spherical variety is determined by its colored fan. A colored fan consists of colored cones, and each colored cone is a pair consisting of a cone and a set of colors. So for a toroidal variety, this set of colors is always empty. That's why they are called colorless. So this is an explanation for the terminology. And what I can say about toroidal varieties, so since toric varieties are well understood, the geometry of toroidal varieties is understood better than in general spherical case. For instance, we have the following smoothness criterion for a toroidal variety. Excuse me, I have to erase this. This was some previous.
Professor.
Yeah.
Well, why didn't affine space a toric variety?
Why affine space is a toric variety? Just imagine the action. So if you have an n-dimensional affine space.
I mean, if we have that the affine space, if the affine space is indeed an affine variety, then the product can be patched together and say that the toroidal variety is locally a toric variety. I mean, there is no reason to write the affine space
well, this is what I just said. This decomposition comes from the previous decomposition. I just wanted to trace back to this kind of decomposition. But of course, you may say that you may formulate this statement by erasing this first factor, because this product is also an affine toric variety. This is what I just, well, let me write it if you like. Well, it is also isomorphic to an affine toric variety, because a product of two different toric varieties is also a toric variety. You may say like this, yeah. Now, let me formulate a smoothness criterion for toric varieties. So theorem 1. A toroidal variety X. Toroidal variety X is smooth if and only if for any G orbit in X, the respective cone C sub Y, I can forget now about the set of colors because it is empty, and I can just consider this cone C sub Y, is what is called strictly simplicial. This means just that it is generated as a cone by linearly independent vectors, say v1, comma, etc. Vm, which form a part of a basis of the dual weight lattice. So that these vectors are linearly independent means that this cone is simplicial. It is generated by linearly independent vectors. And strict simpliciality means that these vectors are not just linearly independent, but they can be completed to a basis of the dual weight lattice. This means strictly simplicial. So this condition is easily verified. It is an efficient criterion for smoothness of a toroidal variety.
What is strictly simplicial? Or this cone is spanned by?
I just explained this. This means this. Okay.
I see.
Okay. So we start the proof of this theorem by some reductions, by several reductions. So first, by the local structure theorem, we may assume that X coincides with Z. We may assume that X is simple and even coincides with Z. Because we are interested in smoothness, yeah? Question?
Well, why can we since we are interested in smoothness, we can throw out a line.
Exactly. Let me just show you. We are interested in smoothness. So smoothness is a local property. We are interested in smoothness of all these B charts, actually, because their G translates cover the whole X. And this B chart is smooth by means of this product decomposition. This B chart is smooth if and only if Z is smooth, because the first factor is just an affine space. So we reduce the problem to the smoothness of Z. And therefore, we may assume that my X is just Z. Okay? So in other words, we may assume that X is an affine toric variety without loss of generality. We may assume that X is an affine toric variety. Let me make yet another reduction. So consider the cone defining this affine toric variety, this cone C sub y, and consider its linear span. Well, over rational numbers, because we consider the vector space spanned by the weight lattice or the dual weight lattice over rational numbers. Consider the linear span of this cone. It may not coincide with the whole space E spanned by the dual weight lattice. But let me intersect this linear span with the dual weight lattice, and we get a sublattice in lambda star, a sublattice which I denote by lambda star naught. So maybe let me draw a picture for you like this. So we have, excuse me, maybe thinner. We have this linear span. We have this linear span. In this linear span, we have the cone C sub y. Let it be, for instance, this cone. This is the cone C sub y. well, let me put it in blue. We have a lattice, the set of lattice vectors in this linear span. This is lambda naught. I don't know, maybe I can mark this lattice vectors by dots. This is lambda naught. Okay. And also I have the complementary lattice, which spans the complementary subspace. Let me denote. Let me indicate this subspace by a line here, like this. Well, maybe this could be bigger. So this is the complementary line. This is the origin. And on this complementary line, of course, I have also lattice points, lattice vectors, like here, 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 and here. And this gives me the complementary sublattice. We can decompose the whole dual weight lattice, lambda star, as a direct sum of lambda naught star and some complementary sublattice, say lambda 1 star. Okay. This gives rise also to a decomposition of the weight lattice itself. So taking the duals, we have the decomposition of the weight lattice lambda as a direct sum of lambda naught, of a sublattice lambda naught, and some complementary sublattice lambda 1. And this gives rise to a decomposition of the torus T, the torus for which Z is a toric variety. The torus T, and lambda is, of course, the character lattice of this torus T. This decomposition of the character lattice gives rise to a decomposition of the torus T into a direct product of two subtori, T naught, corresponding to lambda naught, and T1, corresponding to lambda 1. And also, since the cone defining my toric variety X, the cone defining my affine toric variety X, is contained entirely in the linear span of lambda naught star, we have the decomposition of X, which is now an affine toric variety, as a product of some affine toric variety with respect to T naught, corresponding to the same cone, of course, and the whole T1. Thus, since we are interested in smoothness, and the second factor here, T1, is just an algebraic torus, it is a smooth variety, an algebraic group, we can reduce the smoothness question to X naught. This means that we may assume, go ahead.
So, why do we have the decomposition of lambda star into lambda naught 0 star and lambda?
We can
choose a lambda 1 star, right?
The point is that we can choose the complementary sublattice lambda 1 star in such a way that we have such kind of decomposition. If you have a lattice, and if you have a sublattice,
so this is only choose, no?
Yes. This is a matter of choice. So we can choose, let me write here that we can choose this complementary sublattice. It is not canonical. We can choose it so in many ways, but we can do such a choice. We can make such a choice. Okay?
So why is the decomposition of T induces a decomposition of X?
Because let me recall, for instance, what is the shape of the coordinate algebra of x, if x is a toric variety? So let me write it here. So the coordinate excuse me. Let me put it in black. So the coordinate algebra of x is the direct sum of eigenspaces corresponding to eigenweights in the dual cone. So let me denote this cone just by C for brevity, like this. Okay? Since the cone C is contained in this subspace, the dual cone is a product of a dual cone for C in this subspace and the whole complementary subspace. Okay, so if you take the dual cone of this guy in the whole space, you get a product of the dual of this cone in the subspace and the whole complementary subspace. Okay, and this decomposition of the dual cone as a product gives rise to a decomposition of this coordinate algebra, which is just a semigroup algebra for the semigroup of lattice vectors in this cone. This algebra decomposes as a tensor product. Let me write it here. As a tensor product, excuse me, of two summands. So the first summand is this span over lambda sitting in C check intersect with lambda naught. And the second tensor factor is the product of, is the sum of these eigenspaces corresponding to lambda in lambda 1. Okay? So the first tensor factor is exactly the coordinate algebra of x naught. And the second tensor factor is exactly the coordinate algebra of the torus T1. This gives you a tensor product decomposition for the coordinate algebra, and on the geometric level, this gives you this direct product decomposition for the variety x. Okay?
So since C check since lambda is generated by lambda naught and lambda 1, we have this tensor product decomposition.
Exactly. And since this cone sits in the space spanned by lambda naught star, because of this, we have this kind of composition.
Since the cone is lies in lambda naught star, so we have the first factor equal to some x naught. I want to ask, why is the second factor the whole T1? I mean,
well, just because this is the decomposition of the coordinate algebra of a torus. The coordinate algebra of a torus is decomposed as the direct sum of all spaces spanned by characters, and the characters are exactly the eigenfunctions for the torus. So
wait. So the second factor, we do not need that lambda is inside C check. Why?
Because all these vectors are in C check, because C check in this is in this subspace, and all vectors in its annihilator in the dual space. So it is not a complementary subspace in the same space, it is in the dual space. So you have to imagine, so this is a picture in the space spanned by lambda star. And yes, for the dual cone, you have to imagine the picture in the dual vector space. But since we have this kind of direct product decomposition, we can identify the dual space of lambda star as the direct sum of the dual space of these two guys. Okay? So everything is decomposed in a direct sum. And if we take the dual of this cone in here, well, in the vector space spanned by this lattice, of course, if you take the dual of this cone in here, then we get the direct sum of the dual in here and a part of the dual cone sitting in here. But all vectors in here are dual to C because they vanish. Their pairing with any vector from here is 0. Okay.
Yes. Yes.
And this means that all lattice vectors in here are in the dual cone. So therefore, we take the whole lambda1 here. Okay.
Oh, I see. I see.
Yeah. Okay. Well, so this implies, since we are again interested in smoothness, we can discuss, we are interested in smoothness of X, and this picture reduces everything to the smoothness of X naught. So we may assume that X coincides with X naught without loss of generality. That means that we may assume that the cone C, C is just Cy, this is my short notation, that this cone is solid. It is of full dimension. Because it is of full dimension in this subspace. This subspace is generated by this cone, yeah? And this second factor can be eliminated. The second factor can be eliminated. So we can assume that this cone is solid. And this implies that the dual cone is pointed. Therefore, the dual cone, C check, is then pointed. So we reduce the smoothness question to an affine toric variety for which the the cone defining this affine toric variety is solid and the dual cone is pointed. This is our reduction. Okay? And now let's consider again the coordinate algebra of this affine toric variety. As I already wrote before, it is the direct sum of all eigenspaces corresponding to lattice vectors in the dual cone. Now it is pointed. Okay. This algebra is finitely generated because it is a coordinate algebra on an affine variety. And we may assume that it is generated by eigenvectors, eigenfunctions, f lambda 1, etc., f lambda m, where this lambda 1, lambda m are just all indecomposable vectors in the semigroup of lattice vectors in this cone. All indecomposable vectors. Indecomposable means that they cannot be decomposed as a sum of two other vectors from here. They are, in a sense, minimal elements of the semigroup. And there are finitely many of them because we know that this semigroup is finitely generated. And of course, if there are indecomposable vectors, they cannot be expressed in terms of any other generators. So all indecomposable vectors have to be included in the set of generators. And since the semigroup is finitely generated, so there should be finitely many indecomposable vectors, and all other vectors are expressed in terms of this. This means that this finite generating sets, that this finite set of all indecomposable vectors in this lattice semigroup actually generates the whole semigroup, and the respective functions generate the whole algebra. So maybe it would be instructive to draw a picture again for you. For instance, if this cone C check looks like this, for instance, let me start from here. For instance, take this line. and maybe this line. So this is the cone C check. Let me put it in yellow, brush it in yellow. This is the cone C check, an example of it.
Well, wait, Professor, this C is CY, right?
Excuse me? C is CY, yes. C is CY, yes. C is CY, right. So this is the cone C check. These are the lattice vectors in this cone. Here, here, here. Yeah, all these are lattice vectors. And in decomposable vectors, let me mark it by red, are those this one, and this one. Yeah. So these are the only indecomposable vectors in the lattice semigroup. I don't mark the origin because the origin is just a neutral element of the semigroup. It corresponds to the constant function in this algebra. So this is a special element. And these red dots mark the indecomposable vectors. Okay. So we have this coordinate algebra with a set of generators. And in this coordinate algebra, we have an ideal. We have an ideal, the vanishing ideal of the closed orbit Y. So since our variety is affine toric varieties, it has a unique closed orbit. And what is this vanishing ideal? So we know that to find a vanishing ideal of the closed orbit, we have to take a vector in the relative interior of the cone C and take all vectors in the dual cone which take positive values, whose pairing with this vector in the relative interior is positive. Yeah, and these vectors give us semi-invariant functions in the vanishing ideal because the pairing is exactly the vanishing order along some along the divisor, which is the blow up of this orbit Y. So we have already discussed this. I will not repeat this in detail. So what I say is that this vanishing ideal is just the direct sum of eigenspaces corresponding to all non-zero vectors in this lattice semigroup. Because this cone is pointed, and therefore, if we take a vector in the interior of the dual cone, then it will take a positive value with all vectors in the cone C check, except for the origin, since this cone is pointed. So this is this ideal, and we see that this ideal is just a maximal ideal in this algebra, generated by as an ideal generated by all these functions f lambda 1, f lambda m. It is a maximal ideal. Since it is a maximal ideal, the variety which it defines is a single point. So in this case, if this cone C check is pointed, we get that the closed orbit in Y, in X, the closed orbit in X, this Y is a single point. Say small y, because its vanishing ideal is maximal. And now we are ready to prove the theorem. So one direction. These were the reductions, and now we are ready to prove the theorem. One direction. Suppose that X is smooth. We want to prove that the cone is strictly simplicial. So let's consider this fixed point Y, And let's consider the Zariski tangent space at this point. Actually, we are interested in the dual space, in the cotangent space. Okay? So, as we know from algebraic geometry, this cotangent space is identified with the quotient space of this ideal I modulo its square. And since this ideal is generated by these functions corresponding to all the indecomposable vectors in the lattice semigroup of the cone C check, its square is generated by the functions corresponding to pairwise summands of these lambdas. Yeah, and if you take the quotient, then you get just the vector space generated by the cosets of this lambda of these functions, f lambda 1, f lambda m, modulo the square of this ideal, or in other words, the differentials of these functions at the point y. So the cotangent space is the linear span of the differentials of these functions at lambda y, at y. And actually, these differentials form a basis for the cotangent space. This is a basis. For instance, because they are non-zero and their eigenweights are linearly are different. So they are eigenvectors with distinct eigenweights. And all they are non-zero because these lambdas are indecomposable. So these functions do not belong to the square of this ideal. Okay. And now we see that if x is smooth, if x is smooth, then smoothness means that the dimensions of all tangent spaces at all points are the same as the dimension of x. In particular, this implies that the dimension of the Zariski tangent space at y coincides with the dimension of x. But this dimension is exactly m in the above notation. And this dimension is the rank of the weight lattice, lambda. So we get that the minimal generating set of the semigroup, consists exactly of as many vectors as is the rank of lambda. In other words, these linearly independent vectors, these vectors lambda 1, lambda m should be linearly independent, and they should generate the whole semigroup of lattice vectors in here, in this cone. In other words, this should be a part of a basis of lambda. So this implies that the set of indecomposable vectors, indecomposable lattice vectors in this cone is, well, in this case, it is even a basis because the cone is of full dimension. It is a basis of lambda.
Well, Professor.
Yeah.
So we have that the dimension of Ty of the tangent space is equal to the dimension of x. Well,
this is because of smoothness. This is because of smoothness.
I know this. Well, how do we know that it is a basis of lambda? I mean,
well, because from this equality we know that these vectors lambda 1, lambda m, which are marked here by red dots, for example.
Yes.
There are as many of these vectors as the rank of lambda is. And also these vectors generate all lattice vectors in this cone. So they are linearly independent. There are as many of them as the rank of lambda is. And also they generate all other lattice vectors in this cone. This means that they are a basis of this lattice.
So the cone generated by them is a sublattice of lambda, and their dimension are the same. So
yes.
Oh, yes, I know.
Okay. Well, let me finish this part of the proof. So this means, by definition, that the cone C check is strictly simplicial. And this in turn means that the cone C itself, which is dual to C check, is also strictly simplicial. So we have proved the direction from the left to the right in the theorem. And the direction from the right to the left is even easier. If we know that C is strictly simplicial, and it is also pointed at solid by our reduction, C is strictly simplicial. This implies that C check is also strictly simplicial. And we can choose coordinates on our torus. Choose coordinates. Say T1, Tm. On T, on our torus T, corresponding to the basis lambda 1, lambda m of this indecomposable lattice vectors in the cone C check, to the basis lambda 1, lambda m of lambda. So in such a way that Ti, we can choose coordinates in such a way that Ti is the value of a character lambda I at an element T, which we denoted in this exponential notation like this. So again, let me show you the picture as usual. It is something like this. So you have the basis of the lattice lambda given by indecomposable elements lattice vectors in the cone C check. We can choose coordinates corresponding to this basis. So this is like, I mean, something like this. So excuse me. Yeah. So maybe this would be the basis vectors. This would be our lambda i's. And let me again mark by dots all other lattice vectors. Well, maybe not all of them, but at some distance from the origin. All other lattice vectors in this cone. Okay, so this is my cone C check. Let me again put it in yellow. The cone C check and its generators, which generate also the lattice semigroup of this cone, like this. And now if we choose the coordinates in this way, then we immediately see that the coordinate algebra of X is just a polynomial algebra in these indeterminates, in these coordinates. It is just a polynomial algebra in T1, Tm. Because looking back at the previous page, we see that this coordinate algebra is generated by monomials corresponding to these basic characters, lambda 1, lambda m. And these basic characters are just the variables ti themselves. So we get a polynomial algebra. And of course, the spectrum of this polynomial algebra, that is the variety x, is nothing but an affine space. It is a smooth toric variety, so we have proved smoothness. And this finishes the proof of the theorem, of the smoothness criterion. Now I will stop the first half of my lecture. It is time to make a break, and if you have questions, then please.
See the last page. Sorry.
Just a moment. Let me brush this end of proof square, end of proof sign. Okay.
Okay. So, so I want to ask, when do we have that the vanishing ideal of y is equal to this maximum ideal? I mean, y should correspond to the largest G invariant ideal inside the coordinate ring. I mean,
well, I mean, it is obviously the largest, the maximal ideal. Well, because in this sum we have all these summands except a single one, except the one corresponding to 0. That is, except of scalars. Yeah. So if lambda is 0, then this is just scalars. So the complementary.
Why did the first equality? Well, the vanishing ideal of y is equal to the sum of non-zero.
This one.
Well,
this one.
Yes.
Well, for this, you have to remember, you have to recall how do you construct the ideal of an orbit in a toric variety corresponding to in terms of the cone. Well, for instance, let me say like this. So this vanishing ideal consists of all functions. Well, first of all, it is spent, since it is invariant, it is spent by sum of eigenvectors, yeah, by sum of these f lambdas.
Yes,
Not all of them, but some of them.
And it is the smallest closed orbit, so it corresponds to the largest.
Yes,
ideal.
of course. Yes, of course. You can say that these functions have the following property. So if such a function vanishes at the closed orbit, then it vanishes on some divisor containing this closed orbit. And all divisors, all invariant divisors, all t-stable divisors containing the closed orbit correspond to extremal rays of the dual cone C. So the condition is that this lambda must have positive pairing with at least one of the extremal rays of the dual cone. I mean, not of C check, but of the dual cone. But every lambda in C check has a positive pairing, with at least one of the extremal rays of C, because C is pointed, and C check is also pointed. Okay, this is just from.
Well. Sorry. So if so we must use the fact that the C check is pointed.
Yes.
Right?
Yes. Well, you can even say easier. So clearly, this direct sum is an ideal. Do you agree with this? Because this cone is pointed, and when you take these generators, then you can never get 0 by adding some weight to this generator.
Yes. I know.
So this is a t-stable ideal, and also it is a maximal ideal, because because it is the direct sum of eigenspaces. And since it is a maximal ideal, and since it is t-stable, it corresponds to some orbit, and this orbit is a minimal one. There are no smaller orbits. Yeah?
Yes, I know this.
But you know also that on an affine toric variety, there exists a single minimal orbit, the unique closed orbit.
I was using this route to contain that. Well, I was confused about your initial way. To
explain this, yeah, the initial.
Well, your method does not require that X is a toric variety, right? Or
well, we discussed speaking about general spherical varieties. We discussed sometime before how to describe B semi-invariant functions which vanish on a given orbit Y. Their eigenweights.
Well, I just want to ask. Well, when we describe this, I think I have found some.
Okay.
Well, I have found some notes that we have discussed.
Okay.
Well, I still want to know about in which class do we discuss this. Well, I have difficulty finding my notes.
Okay, no problem. If you have if you will have further questions concerning your notes or whatever, then we can discuss this later. No problem.
And why? Oh, so the implication.
This one.
No, this one is actually smooth. That implies it is strictly spatial, right? Oh, yes.
Yeah.
Well, up to the next page.
This is even easier. If C is strictly simplicial, if the column is strictly simplicial, then you just prove that X is an affine space. By the way, you have proved that affine smooth toric varieties are exactly affine spaces. Every affine. No.
So these coordinates are algebraically independent. So X is
yes, of course, because these lambdas are basic vectors in the character lattice. These coordinates are algebraically independent because this is a basis.
Yes, I see.
Okay, good. Well, by the way, we have to discuss the date of the exam. I don't know, is Huhan here? Huhan, are you here with us? I don't hear him. Maybe he has made a break also. So, but anyway, we have to choose the date of an exam, as Huhan told me. So I don't know how many of you are going to pass the exam. Maybe I will ask Huhan to make a query and to get a list of those of you who want to pass the exam. But anyway, if you want to pass the exam, how many time you need to prepare for the exam? Because I don't think
we have an exam time for 2 weeks.
2 weeks, yeah.
Because exam time for 2 weeks. In those 2 weeks, we have the exam of all the courses we.
I see. So your exam session starts in 2 weeks, right?
What? No. Well, I mean our exam session lasts for 2 weeks.
And when it starts?
Oh well, I think it starts at about June the 20th. I will look at the calendar.
It starts at June 20th, yeah? You say it starts at June 20th.
About June 20th. I mean, well,
okay.
No. It starts about June the 12th.
Okay. So it starts about June 12th and ends somewhat about June 22nd or so, yeah?
25th.
25th. Okay. So you have 2 weeks for your exams starting from June 12th, yeah? Well,
yes.
I think that starting from this Wednesday, from May 17th till June 12th, you have enough time to prepare. A bit less than a month, yeah? I think that it is enough to prepare for the exam.
Well, there are enough, but we may have some exam starting from June the 12th. So
I understand. Of course, you have other exams. I understand this. But what I want to say is that actually we may choose any date starting from June 12th till June 25th for your convenience. I have no special preferences on the date, except for maybe the 15th is not good for me. So I just wanted to figure out the time which we need for preparation for the exam.
So what will the exam proceed? Well, are you going to send us the paper through email or something, or?
Well, maybe we shall discuss the direct procedure because it is distant. We have to figure out what the procedure should be. I have to discuss this maybe with Huhan. I don't know so far. I don't know precisely how it will be organized. But in general, I think that the exam, the final grade will consist of two parts. First of all, you have to send me solutions to exercises from the homework, which I give from time to time during the lectures. Yeah, this is the first thing. Maybe I will single out some list of mandatory exercises, not maybe all of them. I will think about it. But in general, you have to send me solutions to exercises. This is the first part of the exam, if you like. And the exam itself, I think that you will receive a theoretical question from the course program. There will be a list of such questions. I will prepare such a list. And you will receive a question for preparation, say 1 hour for preparation. And after that, you will tell me, you will explain me this part of the course in details according to what you have prepared. I will ask you maybe some questions, maybe some short additional questions, and this will conclude the exam, something like this. But the precise procedure, I have to figure out this procedure with Huhan. I just described how I see it in general, but concrete, precise instructions, you will receive precise instructions later, I think. Okay? Okay. So, by the way, I see that the break time is over and we can continue. So we have proved the smoothness criterion for a toroidal spherical variety. It is very easy in terms of its fan. I don't use the word colored fan here because there are no colors essentially. So we have proved a smoothness criterion. And also let me say that there are criteria of smoothness for general spherical varieties, but they are more complicated. So I will not discuss them in this course. So toroidal varieties, as you see, toroidal varieties are especially nice, an especially nice subclass of spherical varieties. And luckily, there are sufficiently many of them. There is a following theorem due to Michel Brion and Franz Pauer. Let me formulate this theorem. So theorem 2, due to Brion and Pauer. Well, it essentially goes back to Brion and Pauer, though they did not formulate this theorem as it is, as I do it now in their paper. But essentially, it is due to them. In their paper of 1987, the theorem says that given a spherical variety X, given a spherical G variety X, there exists a G equivariant birational map onto X, a G-equivariant proper birational map. It is important that this map is proper. Let me insert it here. G-equivariant proper birational map onto X.
Here mean? Well,
huh?
What do proper here mean? Well,
proper in the sense of algebraic geometry. I mean that is universally closed.
Oh,
that it is closed.
I remember that.
Okay. So onto X from some toroidal variety. So X prime is some toroidal variety. And this map just extends the identity map on the open orbit. So we have an open orbit in here and in here. It is just the same orbit, one and the same. So both varieties are embeddings of one and the same homogeneous space. Why not? And this birational map just extends the identity map on the open orbit. We have already seen such kind of pictures before. So essentially, in other words, every spherical variety is dominated by a toroidal one. This is what this theorem says. Okay? In this sense, there are sufficiently many toroidal varieties. For any spherical homogeneous space, we have sufficiently many toroidal embeddings of this homogeneous space. Every embedding is dominated by a toroidal one. Let us prove this theorem.
Professor, I want to see the last page. I have some. Oh, thanks.
Okay. So let us prove this theorem. Consider the set of all colors on the homogeneous space Y0. And consider the sum of all colors may be taken with some multiplicity. So let us consider the divisor, delta, which is the sum of all colors. So D runs over the set of colors with some multiplicity M. So you know that this multiplicity is usually taken to guarantee that the group action, the G action on Y0 or on X, on whatever, lifts to the line bundle corresponding to this divisor. If you take a sufficiently big multiple, then this always holds. So this divisor is Cartier on the open orbit. Because it is smooth, the open orbit is smooth, so any divisor is Cartier. And therefore, it gives rise to a line bundle over Y0 with canonical B semi-invariant section. So you get a section, write it somewhere here. You get a section S delta of the line bundle over Y0 corresponding to this Cartier divisor delta. And this section is B semi-invariant because delta is B invariant, delta is B stable. Okay? This section S delta is actually a highest weight vector in this section space. And it generates a simple G submodule in the space of sections, which I denote by M. M is just the linear span of the G orbit of this section S delta in the space of sections. Okay, this is a simple G submodule with highest weight vector S delta. And this submodule gives rise to a rational G equivariant map. Yeah.
S theta is just a choice, right? Not a unique or something. Or
well, I mean, this construction.
well, because delta is B stable. Oh, I see.
Delta is B stable, and this section is unique up to a multiple. Actually.
Yes, I see.
Yeah. So this gives rise, as we know, this gives rise to a map, say phi, from the homogeneous space Y naught, to the dual, to the projectivization of the dual space M star, on this projective space, the elements of M are just projective coordinates. So since we have this inclusion, this gives rise to this map. And of course, this map can be viewed, can be extended, if you like, to a G-equivariant rational map from X. So our variety X is an open embedding of X naught. And this map from Y of Y naught, and this map from Y naught to P of M star can be viewed as a rational map from X to this projective space. Now let's consider the graph of this map. That is, you consider the product. You consider the product of X and this projective space. Yeah. And you consider the rational map from X to this product. Which I denote by big phi. Maybe write it here, big phi. Which is just the product map. On the first factor, we have the identity map. And on the second factor, we have the map phi. So we get a map from here to here. And the initial map phi is the composition of this big phi and the projection onto the second factor here. So we have this commutative diagram. From here to here, we have the projection map. And this map big phi, when restricted on Y naught, this map big phi is just an extension of, well, this map gives you an inclusion of Y naught into this product variety. Because on Y naught, this map is well defined. It is regular on Y naught. And therefore, you just have the identity map on the first factor, which gives you the injection, and the map phi on the second factor. So this Y naught is included into this product variety as the graph of the map small phi from here to here. Now, let's consider the closure of this map big phi. This is a subvariety in here. And this subvariety is still an open embedding of Y naught. Because this map from Y naught to this guy is a closed, is an embedding. And this identifies Y naught with an open subvariety in its closure in here. So this guy is again an open embedding, an open G-equivariant embedding of Y naught. It may be non-normal, but you can normalize it. Let us normalize, and then we get the variety X prime. So this map is just the normalization map. And you get the variety X prime, which is already normal. It is still an open embedding of Y naught. It is a spherical variety. It is already normal. And we have two maps, two projections. So the projection onto X and the projection to pi of m star, to p of m star, to the projectivization of m star, because x prime is mapped onto here, and this is a subset in here, so we have two projections on x and on p of m star. So the first projection is a proper birational map. Proper and birational map, because it is a projection along the projective space. The projective space is complete, and the projection along it from a product variety to the first factor is proper. The projection from here to here is proper. So this map is proper and birational, because on the open orbit y naught it is just the identity map, and this map is extending. This map is extending the map phi on the open orbit. So let me denote it as phi prime. Phi prime is an extension of phi. Okay, so we have such kind of picture.
Professor, I think projection along a projective variety is closed. Well, how can we know that?
Not only closed, it is even stronger than closed. It is a proper map. A projection along a projective variety is a proper map. In particular, it is closed, of course, but it is a weaker property.
So if we only have complete, we only have closed. But if we have projective, we have proper.
No. Even if we have complete, then this map is proper, because it remains closed under changing the base. If you make a base change for this map, then it will still be a projection along PM star. Okay. The projection, so it is a basic statement in algebraic geometry that the projection along a complete variety is a proper map. Okay. In particular, it is closed. Okay. Well, what does this picture gives us? I mean, this picture. This picture here. Well, it gives us, in particular, that the line bundle corresponding to the divisor delta, which we use to construct this map. Yeah. So we constructed this map phi in such a way that the line bundle O of delta is the pullback of the canonical ample line bundle on this projective space, the pullback of O of 1. Yeah. So since this map phi from here to here extends to x prime, then this line bundle can be extended to a line bundle over x prime. So this implies that O of delta extends to a line bundle, say L over x prime. And the space of sections M, this G submodule, can be viewed as a subspace of section of this extended line bundle. So we can say that M is embedded in the space of sections, is contained in the space of sections already of the extended line bundle, not over y naught, but over the whole x prime. Because we have a regular map from here to here, and this means that the sections from M are regular over x prime. They are just pullbacks of hyperplane of linear forms on this projective space, yeah, in projective coordinates. So we have this inclusion, and also let me indicate that, of course, it is already on the picture. Let me indicate that this map phi prime is regular on x prime. Is regular. And this means that phi prime is regular means that for any point in X prime, there exists a section from here which does not.
Oh, this is regular since the projection is regular.
Yes, yes, yes. Because of this construction. This is a regular map, and this is just a subvariety in here. Well, after normalization, so this map is a composition of this one and the projection here. Yeah, but still it is a regular map as a composition of two regular maps. Okay. Since this phi prime is regular, for any point in X prime, its image is in this projective space, and some of the projective coordinates on here do not vanish at this point. This means that some of sections from M do not vanish at this point. Let me write it on the next page. So this implies that for any X in X prime, there exists a section in this M which does not vanish at X. But all sections in M are linear combinations of G shifts of this section. So we can write that there exists a G shift of the section S delta. So there exists G in big G such that the G shift of S delta does not vanish at X. And this implies, of course, that the section S delta itself does not vanish at the G inverse shift of X. So, in other words, the vanishing locus of S delta on X prime on X prime does not contain any G orbit. So you have started from any point in X prime, yeah? And you have proved that this section S delta does not vanish at some point in the G orbit of X, of this point X. Therefore, the vanishing locus of S delta does not contain any G orbit. In particular, it does not contain any G stable prime divisor on X prime. And therefore, this vanishing locus is just the union of all colors. Well, maybe I should write here. So here we consider the colors on the homogeneous space, and now I'm considering the colors on X prime, which is an embedding of Y naught. So these colors on X prime are, of course, identified. These colors on X prime are identified with the colors of Y naught by taking the closures. So it will be more safe to write here like this. So the vanishing locus of S delta is the union of closures. Of all colors on my homogeneous space Y naught. Yeah, okay. Because it was so on Y naught. On Y naught, we had that this S delta corresponds to this divisor, which is that the sum of all colors with some multiple. Yeah. So the vanishing locus of S delta on Y naught is exactly the union of all colors. And what we have proved here is that when we pass from Y naught to its embedding, X prime, adding some extra orbits, then this vanishing locus does not contain any of these orbits. So essentially, this vanishing locus is just the closure of the vanishing locus of Y naught. This means, of course, this implies that X prime is toroidal. Because the union of all colors on X prime does not contain any G orbit. So the theorem is proven. Okay, questions?
The last page where I want to see.
Just a moment. So you see that
the proper map restricted to a subvariety is still proper.
Yes. Well, restricted to a closed subvariety. Restricted to a closed subvariety is still proper. Yeah.
And composite with a normalization is still proper.
Yes, because normalization is a finite map. In particular, it is proper. The composition of two proper maps is still proper. Yes, these are basic things from algebraic geometry. I have no time to discuss it in details, but it is true. Yeah. Okay. Okay. Well, let's go further. This theorem saying that every spherical variety is dominated by a toroidal one has an interesting corollary. As a corollary, we can prove that the evaluation cone is a polyhedral cone. This is also due to Brionen power. So the proof is as follows. So we have a spherical homogeneous space Y0, for which we consider this valuation cone, and we can choose a complete open embedding of this Y0. Choose a complete, even projective, but this is not essential. Choose a complete open embedding X of Y0. Why we can choose such an embedding? Well, we know that Y0 is a homogeneous space, it is quasi-projective, and therefore we can embed Y0 into some projective space. There is an equivariant embedding of Y0 in a projective space. Then we may take the projective closure of this embedded Y0. We get a projective variety containing Y0. It may be non-normal, but we can take a normalization and we get a projective normal variety containing Y0 as an open orbit. So it is not a problem to choose such an embedding. Now, using the previous theorem, we may even assume that X is toroidal. If X were not toroidal, then we could replace X by its toroidal dominating variety X prime, by this X prime. If X were not toroidal, we could replace X with X prime. Since X were complete and this map is proper, then X prime would be also complete. Okay? Now, we have a completeness criterion. By a completeness criterion, we know that the valuation cone is covered by the cones corresponding to all orbits, to all G orbits in X. And since X is toroidal, we can even say that the valuation cone is equal to the union of all these cones. Indeed, it is covered by this union, so we have an inclusion of this into this. But since X is toroidal, there are no colors containing the orbit Y, and therefore this cone is generated by the vectors corresponding to G-stable prime divisors containing y. So these vectors are from the valuation cone. Each of these cones, Cy, is contained in the valuation cone.
Oh, completeness means that the color reference covers the whole valuation cone.
Yes, this is our completeness criterion, which we have proved sometime before. Yeah. So completeness, let me move it somewhat here. Completeness means that this guy is included in this union. But since each of these cones is generated by some vectors from here, corresponding to the G-stable prime divisors containing y, each of these cones is generated by some vectors from here. It is already included in V, in the valuation cone. And therefore, we have not just an inclusion here, we have an equality. We have equality. Well, and since V is a convex cone and it is a union of polyhedral cones, of finitely many polyhedral cones, each of these cones is a polyhedral cone. So these are polyhedral cones.
Oh, since there is no color, so there is a so Cy is contained in valuation cone. Oh, I see.
Yes, yes, yes. These guys are polyhedral cones, and V is a finite union of polyhedral cones. Hence, it is also polyhedral.
Well, I think we have said many courses ago that V is also a co-simplicial cone. Well, we cannot.
Yes, I mean, yes. Let me again make this remark. Yeah, you are right. Let me again put this remark here. But this I will not prove. Let me put a remark that there is even a more precise statement about this valuation cone. Let me put it on the next line. Remark. In fact, V is even a cosimplicial cone. Not just a polyhedral cone, but even a cosimplicial cone. The reason is that V is a fundamental domain. For some finite reflection group. Let me denote it as VW sub X, thinking about the while group, of course. A finite reflection group which acts on the vector space, spanned by the dual of the weight lattice, which is generated by reflections in this vector space, and which preserves the weight lattice. So it is a subgroup in the group of linear transformations of the dual weight lattice. This group is called the little while group. Of a spherical variety X. This is a deep result due to Brion and Knopp, and the proof is complicated, so I won't discuss it in this lecture course. But this is also true. Just to let you know that the structure of the evaluation cone can be made more precise. So since V is a polyhedral cone, you can easily construct toroidal embeddings and even complete toroidal embeddings by choosing a subdivision of this valuation cone in the union of cones, of polyhedral cones intersecting along faces. Which is a fan in the usual sense, say in the sense of toric geometry. So you can construct toroidal varieties by taking fans in the valuation cone. Okay. Well, at the end of this lecture, we shall turn, we have discussed toroidal varieties, and at the end of this lecture, we turn to divisors and line bundles on spherical varieties. Divisors and line bundles on spherical varieties. This theory is actually well developed, mainly by the work of Michel Brion. For instance, one can prove that each divisor is equivalent modulo principal divisors to a bistable one. There are criteria for a bistable divisor to be Cartier or ample. There is a presentation for the Picard group of a spherical variety by generators and relations, and so on. Actually, it is not hard to develop all these things from what we already know about spherical varieties. But because of the lack of time, I have to be selective. So I only consider the G-module structure of the space of sections of a line bundle over a spherical variety. So let me use the following notation. So suppose, again, that X is a spherical variety. Spherical G variety. Let me denote by D1, etc., ds, all the B-stable prime divisors, both colors and G-stable prime divisors. I do not distinguish between them now. The B-stable prime divisors on X. And let Vi denote the corresponding vectors in the dual weight lattice. So Vi is Vdi bar in our notation. The vectors in the dual of the weight lattice. Okay? Now let's consider a G-line bundle over X. So let L be a G-line bundle, a line bundle equipped with the action on G lifted from the action on X. Then we have the space of sections of this line bundle, and this space of sections is a G module. And let us choose an arbitrary highest weight vector in this G module. So let S naught be a highest weight vector in the space of sections of this line bundle L. Say of highest weight lambda naught. Okay? Consider the divisor delta of this section. It is a B-stable divisor, and therefore it is decomposed as a linear combination of these di's. So it is a sum over all i's of di's with some multiples, with some multiplicities. Like this. Okay? Now let me denote by, so let me put it here. Let me denote by script P, or if you like, P of delta. It depends on delta. The set of all vectors in the dual space E star, which is just the linear span of the weight lattice. Let me recall that it is just the linear span of the weight lattice over rational numbers. Well, over rational numbers, you can even take, yeah, let it be over rational numbers. The set of all vectors in E star which satisfy the following inequalities. So the pairing of this lambda with each of vi's, the pairing of vi with lambda, is greater or equal than minus mi for any I. For any I from 1 to s. Okay? So this set P is given by a finite set of linear inequalities on lambda, yeah? So this is a polyhedral domain. This P is a polyhedral domain. Polyhedral domain in this vector space E star. May be unbounded. So this set of inequalities may define an unbounded polyhedral domain, or maybe bounded. Sometimes it is a bounded polyhedral. Let me maybe give you an illustration, a picture again, as I usually do. So here is a picture. For instance, like this. I don't know. Let me start from here. Well, maybe let's start from somewhere here. Excuse me. Thinner. What I want to do like this. Yeah. Yeah. So this is a hyperplane defining the first linear inequality. This is a hyperplane defining another linear inequality. Then yet another one. Like this. For instance, yet another one. Oops, excuse me. Let me pick this. Yeah, like this. So this is my P. Let me put it in some color. For instance, in blue. Something like this. And these hyperplanes given by lines, indicated by lines here, just denote the supporting hyperplanes given by these linear inequalities. So the vectors vi are the normal vectors to this hyperplane. So let me draw them somewhere here. I don't know, like this maybe. So, excuse me, in black. This vector, this vector, this vector. These are normal vectors, so these are these vi's. And what is defined by these inequalities is our polyhedral domain P. So this is the picture. Okay. And now the theorem. Well, maybe the proposition, it is quite easy. So let me call it a proposition. Proposition. Due again to Michel Brion. describes the G-module structure of the space of sections of the line bundle L. Namely, as a G-module, the space of sections, so as a G-module, this space of sections is isomorphic to the direct sum of simple G submodules of highest weights of the form lambda plus lambda naught, where lambda naught is the highest weight of the section S naught, which you have seen on the previous slide, and lambda runs over all lattice vectors in this polyhedron P. So if you look at the picture, you have to pick all lattice vectors here, all lattice points in this polyhedron. Let me pick them. This. So there are many of them. But anyway, let me pick them all. Yeah, like this. So all lattice points in this polyhedron, you have to take all these lattice points, shift these points by lambda naught, and consider the irreducible G modules with highest weight lambda plus lambda naught. And the direct sum of all these G modules is isomorphic as a G module to the space of global sections of the line bundle L over the spherical variety X naught. So this is the theorem. And the proof is very short. So let me give you the proof on today's lecture, because I don't want to spend time on the final lecture. And this proof, it is quite short indeed. So let me give you a proof. So recall that the representation of G in the space of sections of a line bundle over a spherical variety is multiplicity free. Is multiplicity free. This means that if we want to describe the G module structure of this representation, it suffices only to indicate the highest weights. Because for each highest weight, there exists a unique irreducible submodule in the space of sections with this highest weight. We can only pick up highest weights which occur in this representation. So let me write down that it suffices to find highest weights. Suppose we have a highest weight vector S in the space of sections. Highest weight vector, B semi-invariant vector of some highest weight mu. Then, since this S is B semi-invariant, it differs from S naught. S differs from S naught by a semi-invariant rational function, f lambda. The ratio of these two sections, both are semi-invariant. S and S naught are both semi-invariant. They differ by a semi-invariant rational function of some eigenweight lambda. And for the weights, we have the following. So the weight of S is the sum of lambda and the weight of S naught. Now also, since S is a regular section, the divisor of S, which can be written as the sum of the divisor of f lambda and the divisor of S naught, which in turn can be written as follows. So the divisor of f lambda is the sum of all these prime b-stable divisors d1, ds with multiplicities which are vanishing orders of this f lambda along these divisors. And the vanishing orders are given by pairings of the weight lambda with these vectors vi. So the divisor of S lambda is of F lambda is of the form the coefficient, which is a pairing of Fi with lambda, times di. And the divisor of S naught is just delta. So since S is a regular section, this divisor has to be effective. All the coefficients should be non-negative. And the coefficients of delta with respect to this decomposition in terms of di's are exactly mi's. The coefficients of delta are these mi's. So we have the following. So each of these pairings plus the respective mi should be non-negative. So this condition that the divisor is effective holds if and only if and only if the pairing of vi with lambda plus mi is non-negative for all i's. And these inequalities are exactly the inequalities defining the polyhedral domain P. Yeah, just look at here. So this holds if and only if lambda belongs to P. All highest weights of sections, all highest weights in this representation space are of this form. And conversely, of course, conversely, we have the same argument. Conversely, any lambda, which is a lattice point in this P, corresponds to some S, which is a highest weight vector in the space of sections corresponding to the highest weight lambda plus lambda naught. This can be seen just by reversing the previous argument. So this proves the theorem, the proposition. Well, I am ready to stop, and the only thing I want to do at the end is to give you an exercise, just an exercise concerning this proposition. So an exercise for you. An exercise for you. Excuse me, I usually do it in the red color. Let me keep this convention. An exercise for you is to do the following. So consider the representation of the special orthogonal group SON in the symmetric power, in the case symmetric power of the n-dimensional vector space k to the n. This is script k to the n on which SON acts naturally. And the exercise is to decompose this representation. Excuse me?
What is SK?
Symmetric power, kth symmetric power. S means symmetric power, kth symmetric power. Okay? This is the kth symmetric power of this vector space script k to the n. So the exercise is to decompose this into irreducible representations. And a hint for solution of this exercise, a hint is to consider the spherical action, of the group SON at the projectivization of this vector space k to the n, so on the n-1 dimensional projective space. prove that this action is spherical, and apply the previous proposition. So this case symmetric power can be viewed as the space of sections of a line bundle of the projective space. And you can use this proposition to decompose this space of sections into irreducibles. This is a hint for solving this exercise. Now I'm stopping. Thank you for your attention. Sorry for taking some time at the end of the lecture. And I'm ready to answer your questions if you have some questions remaining.
Question
you are
about
welcome.
the smooth implies strictly simplicial part.
This part. Yes.
Yes, this part. Well, so when we have the dimension of the tangent space is equal to the rank, I think we only have that lambda 1 to lambda m is a basis of lambda tensors Q. I don't think we can conclude that it's the basis of lambda.
You are right that from this equality, you have that this guy is the basis of the vector space. But recall that this set of vectors is all indecomposable vectors in this column. All indecomposable lattice vectors in this column.
Yes.
So this means that all lattice vectors in this column are integer linear combinations of this lambda 1, lambda n.
Yes.
And this implies that it is a basis of a lattice, in fact.
Why?
Otherwise, you should have a lattice vector which is decomposable as a linear combination of this lambda 1, lambda n, but with rational coefficients.
Yes.
Yeah? But therefore, if its vector cannot be decomposed with integer coefficients, yeah, then it is also indecomposable in this sense. Indecomposable means that cannot be decomposed as a sum of some of this lambda 1, lambda m, yeah? Of some indecomposable means lattice vectors which cannot be decomposed as a sum of lattice vectors in here.
Well, so, why should that vector?
Well, for instance, let me maybe give you just an example. I don't know if it will be convincing, but let me give you an example. So, for instance, suppose we have the following. So, suppose we have I don't know. Suppose we have two vectors, two-dimensional situation. So we have this vector, yeah, and maybe this vector. They form a basis of the vector space, yeah. So this is the column, yeah.
Professor, I mean that yes, well, if it is not the base of lambda, we have a vector in lambda that is a rational combination of lambda I, but not integral combination.
For instance, this one, yeah. For instance, this one.
Yeah. Yes, for instance.
But this vector will be also indecomposable in this sense.
But how can we prove that this vector is contained in C check? I mean, this vector may be outside C check.
Well, if you have a vector outside of C check, then you also have a vector in C check. So, for instance, if you have a vector somewhere here, I don't know, this one, yeah.
Well, C check. I think C check is not.
C check is this. Yeah.
C check is a solid space, or C check
is a solid. Yeah, C check is a solid cone. C check is a solid cone. Yeah.
Well, C check is a solid cone. I want to think about C check is the vertex. The vertex.
It is both. Yeah. Let me say it is both solid and pointed. It is both solid and pointed.
That C check is the integral combination of
No, C check is a cone. C check is a cone.
Combination. Oh, I see.
Yeah. But this guy is integral. This intersection is integral. Yes. But C check is the whole cone. Is it clear now?
Yes, I see.
Okay, good. So, more questions? Questions, comments, whatever.
So if we have a vector outside C check, why do we have an vector inside C check? Yes.
Well, just look at the picture. So you have this vector, yeah? You can add to this vector, for instance, this one, and you get a vector inside C check. And you always can do it, because when you take this vector and you take a cone, if you shift this cone C check by this vector, so you get this cone, yeah?
Yes.
Do you see it?
Yes.
And these cones actually overlap. You have something in here.
Well, this is because C check is solid, right?
Exactly. This is because they both are solid. Exactly.
I see.
Okay, good. So this is some elementary convex geometry. Maybe I skip some elementary arguments, but they are easy to restore if you know something about convex geometry. It is not complicated, absolutely. But of course, if you feel that you do not understand some points, you always can ask me. I will clarify. Other questions? I don't know if Huhan is still with us. Huhan, do you hear us? No, he seems to be away. But I am back about the exams. So we shall discuss. So as you told me, you have your exam session starting from 12th of June and lasting for some 10 days or so. 12 days, I don't remember. 2 weeks, yeah, 2 weeks. So we shall then discuss with Huhan the date of exam in email exchange, and maybe he will make a query for among you to ask you what date of an exam is most convenient for you. So we shall agree about the date of exam. But what I see now is that you have enough, at least you have enough time to prepare. About 3 weeks or so, it is more than enough to prepare. Otherwise, you will forget what you started with. If you will have more time to prepare, then it is not helpful. So I think that we shall fix the date of an exam maybe on the last lecture, or maybe later in email exchange. Anyway, we'll agree about the date. And also on the last lecture, I will, or maybe again later, it depends on what we agree about, I will clarify the procedure of the exam, which I already explained in general today. Well, let me just say that on the final lecture, I'll discuss some applications. I have only one lecture left, but I'll try to discuss some applications of spherical varieties to other problems, to other geometric or representation theoretic problems, which in particular will be based on this Brion's proposition, which we just proved. I mean, this one. If there are no more questions, then let me stop sharing the whiteboard. And I hope to see you all on my last lecture on Wednesday. See you and bye-bye.
By the way, Professor,